So, dear students, very good afternoon to all of you. So, today the topic is time complexity analysis of heap sort along with the algos, which we'll be writing. So, first algo which we did in the previous lecture was heapification. So, heapification is basically to heapify. Actually, the root should contain the maximum element. In order to do that, we just heapified the tree. So this is a tree which is given to us in figure number 1. So this is our parent node, root node, left child, right child. This is again left and right child of 33 respectively. Fine. Now, if I see that root contains the element 12, which is smaller than 33 and 16 as well, that means it is violating the heapification property. So, first of all, we have to heapify it. Um, we have to build either the max heap or min heap. We have to either build the max heap or min heap. So, max heap is the heap where element at the root is greater than the child nodes. Fine, or element at the parent is greater than the item or element at the child node. Fine. So, for that, we'll see. Uh, we'll compare from left to right. 33 is greater than 16. So make 33 as root and 12 will come down and it will become the parent of 4 and 20. And 16 will remain as it is. Now, if you see 12 and 16 are both smaller than 36, that means the elements at the child node are smaller than the parent node. Now, we will take the other elements, that is 4 and 20, which are left and right child of 12 respectively. Again, they are violating the heapify property because right child, that is 20, is greater than the number at the parent, that is 12. So we are going to swap it. So this will be 33 is my parent. This is 20. This is 16. This becomes 12 and this becomes 14. So we have swapped 12 and 20. 20 will become the root node and 12 will become the child node. Fine. So the maximum distance which is covered by any node for the heapification is the height of tree. See, what we have started from the root node 12 and we have moved till the last child, that is 20. And we kept on swapping until we found the until we satisfy the heapification property. That is, every node at the parent is greater than the child nodes. See, 33 is greater than 20 and 16 and 20 is greater than 4 and 12. So the maximum distance which an tree, which a node would cover in order to heapify itself or heapify the tree, entire tree would be the height of tree. It is represented by H. It is represented by H. So height of tree is O log n. This we have done. Complete binary tree is O log 2n for a binary tree. So if heapification is there and we are just swapping the nodes in order to make it a max heap or a min heap, that means it will also take the time which is equal to log n time, since the time is equal to the height of tree, that is O log n is the height of tree. So for a binary tree we need log n comparisons. Here we will also do the log n comparison, so it will take log n time. Log n time. So this is the time for the heapification. So this algo works in three parts. First is heapification or heapify process. Second is build max heap. And third is heap sort. That is the algo which we will make. So this is the first process, that is heapification. I already explained the algo for the heapify process in the previous lecture. So this was the time which was taken by the heapification itself. Now let's do the build heap part. So second part is building of max heap. I'll write the algo, then we will draw the tree and try to trace this algo. See, this is the tree which is given to us. So we will try to follow this algorithm in order to build the max heap. So build max heap a comma n, that is array, the elements which would be passed to this procedure, and n will be the number of elements in the array. Fine, n will be the number of elements, and a is the entire array which will be passed to this I mean procedure. Fine. So we have done the array representation of this heap. So this is kind of like this: 0, 1, 2, 3, 4, 5. That means 12, 33, 16, 4 and 20. Fine. So this is the array representation of a tree which is given to us. For this array will be passed as A, and n will be 5, which will be the number of elements. Now for I is equal to n by 2. Why n by 2? Because these are your non-leaf nodes. The nodes which do not have any children, they are called non-leaf nodes. And this is your leaf node. Okay. So if I omit this and I take this as one more child, or I take this as 3. So I append 24. So this is my leaf node, or we can say this is your last parent. This is your non-leaf node, and this is your last parent. So this is n, and this goes to n by 2. For example, we have total 6 elements. 6 by 2 is 3. So from third node, we'll start heapifying it. So n by 2 is 6 by 2, that is 3. 3 is greater than equal to 1, I minus minus, heapify a I comma n. So start heapifying it according to the heapification process. First of all, heapify the node number 3. Heapify the node number 3. So this will become 12, 33, 24, because we are going to swap it, since we have to heapify. 16 is smaller than 24. So 24 will go up and 16 will come down. So this is being exchanged. So this is this way. Fine. So 16 is the left child of 24. This is how heapification is done. Now I is greater than equal to 1. Yes, because 3 is greater than equal to 1. I minus minus. So now go to node number 2. So heapify it. Now what will happen? 33, 4 and 20. So if we see that 4 and 20 are smaller than 33, so this is already heapified. So we will not do any heapification process on it. Then go to parent node. That is because it should be equal to 1. So go to the parent node. Since we are at a parent node, so perform the heapification 33 and 24. Which is greater? Left child is greater. So swap 12 with the left child. 33, then come here 12. Okay. Now you again see this is again violating the heap property. So 4 is smaller than 20. Okay. But 20 is greater than 12. 20 is greater than 12. So again perform the heapification. That is 20 will come here and 12 will go down. This is how heapification is performed, and it takes how much time? See, this takes n time, because if you take O of n by 2, because you have taken the half of the tree, so this becomes the order of n by 2. And n by 2 is nothing but order of n time. So this loop is going to take order of n time, whereas heapification is taking log of n time, because I have already proved that it is taking log of n time. So this build heap process will take O of n log n time. O of n log n time. Fine. Because n by 2 roughly gives me, if O n by 2 is order of n by 2, then it is equivalent to order of n. Then you will write order of n log n. Okay. So this is how the process I mean, time complexity of build heaps or build heap process is done. Fine. Build heap process is having just one loop statement for I is equal to n by 2, which is roughly equal to order of n by 2, which is equal to order of n. And heapification process takes how much time? Log of n time. So together they make order of n log n time. So build max heap procedure will take order of n log n time. We will try to prove that build heaps will take order of n time only. Okay, because we have just proved that it is taking order of n log n time. But now I will tell you how it is taking only order of n time. So for that, suppose this is a tree which is given to us. This is a tree which is given to us. So here, this is level 0, level 1, level 2, and level 3. This is level 0, level 1, level 2, and level 3. Right? So, see, total time, see how many type of heap, how many times, see these are your non-leaf nodes. These are your non-leaf nodes. They are also involved, non-leaf nodes are also involved in the process of heapification. In heapification process. So here, how many nodes are there? 1, 2, 3, 4. So 4 times heapification will be performed. 4 times heapification will be performed. Here 2 nodes are available. So 2 times heapification will be performed. Here 1 node is available. So 1 time heapification is performed. See, this is 1, 2, and 3, 4, 5, 6, and 7. So 2 times heapification for node 2 as well as node 3. Here heapification for node 1. Then 4, 5, 6, and 7 nodes heapification will be done at this level 1. Here it is level 2 and here it is level 3. Yeah. Oh. So I repeat, this is level 0, level 1, level 2, and level 3. Here 4 nodes are involved. So 4 times heapification process will be done. Here 2 times heapification process will be done. And here 1 time heapification process will be done. So the total time which is taken see as log n is the height of a tree. As log n is the height of a binary tree. So it will take log n time at each level. At each level. Fine. So how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8. So this becomes 8 leaf nodes. So this is your 1 log n time. This is your 2 log n time. This is your 4 log n time. This is your 8 log n time. Fine. Because the heapification process for tree will take log n time. Therefore, this process will take 8 log n time, 4 log n time, 2 log n time, and 1 log n time. Okay. So by covering, see, from first edge, you can go for 3 edges to reach the non-leaf node, or vice versa. By covering 3 edges, you can go to the parent. Similarly, if 2 is a parent, you have to go how many levels down? 2 levels down to reach the last node. Fine. So this is 2 log n time, and this is 4 log n time, because there are 4 nodes and each have 3 number of nodes. So I'll tell you how to calculate the total time. Total time at height h of a tree is equal to number of nodes at that level into log n multiplied by log n. So see, if this is given by formula, h is equal to n upon 2 into h plus 1. So this is level 0. So h height 0 means this thing. H0 means level 0. So n is total number of nodes is 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 nodes are there. So 15 upon 2 into 0 plus 1. Fine. Into log n. So 15 by 1 log n. Okay. So this becomes 2 into 2 power 0 is 0. Plus 1 is 2 power 1. So this becomes 15 upon 2, which is roughly equal to 8. 8 log n time. This is how it is calculated. Then at level 1, 15 upon 2 into 2 plus 1, that is 15 upon 8. I'm calculating this. So it is roughly equal to 2. Now 15 upon 2 raised to power 1 plus 1, which is equal to 15 upon, at level 1. This is at level 2. So this becomes 2 raised to power 2, 15 by 4. So this is roughly equal to 4. So this becomes 4 log n time. This becomes 8 log n time. This becomes 2 log n time. And this becomes 1 log n time. Now, we have to substitute the number of nodes. Instead of n, you have to substitute the number of nodes. See, there are no leaf nodes. These are non-leaf nodes. So individual node is 1. So this will become 1. Here, this tree has how many nodes? 7 has 3 nodes. So 4 nodes with the 3 nodes each. So 4 log 3. 2 nodes with how many nodes? 1, 2, 3, 4, 5, 6 and 7. These are 7 nodes. So instead of this 7. And here you will put 15 because total nodes in this tree are 15. See, 1, 2, 3, 4, 5, 6, 7, 8. So every node is an individual. So this will become 8 log 1. This is 4 log 3 because each tree has 7 has child 14 and 15. So 7 is also included. So this becomes 4 log 3. Here 3, 6, 7, 12, 13, 14 and 15. These become 7 nodes and entire tree becomes the 15 nodes. So you will write this way. And if I calculate this, this is roughly equal to 1 into 3 because this you have to take log base 2. This is like this. So this is 0. This is roughly 4. and because 2 into 2 log base 2 7 is roughly equal to 2, and this is equal to 4. I mean, this is equal to 1. Log base 2 3 is roughly equal to 1, so this becomes 4, and this becomes again 4, and this becomes 3. So this is the total time which would be taken. So let's calculate the total time. If I roughly calculate it, it will become this thing. Sigma, at each level, we are going to add up all these times and we'll get the final time. So this will become sigma of n is equal to 0 to log n, because you have taken the inputs from n0 to log n, and n upon 2 of h plus 1 into big O of h. Right? Because we are taking the height of tree to travel. So you can write this thing as log n equal to n0. This is roughly like this. So you will write 2 upon 2h into 2 raised to power 1, because some constant has to be multiplied whenever we are finding the O. So you will write this thing. Okay. Then bring all the constants outside. It will be n is equal to 0 to log n and 1 upon 2 raised to power h into h, which is roughly equal to, if we apply the harmonic mean here and take the limits to infinity, and apply the harmonic mean for h upon 2h. So it is roughly equal to 2. It is roughly equal to 2. Applying the harmonic mean here, it is roughly equal to 2. Now, c dot n upon 2 into 2, 2 cancels out. So c is a constant. Ignore this constant and this will become order of n. So this will become order of n. So this will become order of n. Now next is the heap sort. This is the final algo for the heap sort. See, again I told you this will take order of n time. This will take order of log n time. This is again on times, or on by 2 times. So n times the statement will work. This is order of log n. Maxify. So I explained the heap sort algorithm. Heap sort A comma n already told you that A is an array of elements and n is the number of elements in the array. So for I is equal to n by 2, we will move to the last parent node in order to heapify this. Once you have heapified, then swapping will occur between the last element and the root element, and you will again call the heapify with the largest number. So heapification first of all will take order of n by 2 time, then order of n log n, order of log n, then n, and order of log n. So if I combine all these, then highest power of n is only 1, so it is order of n, and log n is common. So you can take order of n log n time for the entire heap sort answer. It will take order of n log n for the entire heap sort L. So this is how heap sort analysis is done. Now we are over with it. Now next is priority queue. You can implement heap sort with the help of priority queues. There are two types of heap, or max heap and min heap. Element, larger element, larger priority. Smaller number, larger priority. Priority is nothing but the number itself. Priority is nothing but the number itself. Right? Priority is nothing but the number itself. For example, just we have done the tree. See, this is a max heap. The number which is largest will come out first, right? So 33 is the largest among all these numbers, so it will come out. So if I say extract min max, so this will take the 33 number. Okay. Now if I am going to keep it out, this 16 is going to swap here. Again heapify, and the root node will contain the 26 element. If I remove it, root node will contain the 26 element. This is how the tree will remain after removing the 33. Again, I say extract max. So 26 has the highest priority, so it will come out. Similarly, max heap means larger number, larger priority. The number with the largest priority will come out first, right? And we can implement it. Similarly, if it is a min heap, so 12 is greater than 9 and 10. This is greater than 8 and 7. This is greater than 6 and sorry. See now, 12 is smaller than 20 and 24. 20 is smaller than 45 and 53. And 24 is smaller than 63 and 75. That means this is your min heap. Here, smaller number means larger priority. Smaller number means larger. The smallest number will come out first. 12 will come out first. Then 75 will go up, and again you will satisfy the min heap property. Then after satisfying the min heap property, what you will get? You will get the second smallest number, that is 20 here. Fine. So 20 here. So this will be the decreasing heap or decreasing order. This will be the increasing order. This will be the increasing order. That means we can implement the heaps with the help of priority queues only. Because when we satisfy the max heap and min heap property, that means we are actually implementing the heap, or we are implementing the priority queues using the heap. Here function is extract min or insert min, and heapification will be done in order to satisfy the heap property. Similarly, here extract max and insert max or insert key. You can see these two functions are applicable in the priority queues. So we can implement we actually implement the priority heaps with priority queues only. So binary search is again divide and conquer technique. Fine. So for finding, actually binary search also divides the bigger problem into sub problems. Then the solutions individually are combined to get the final solution. So first of all, we have mid is equal to L plus H by 2. We have to find the mid so that we can divide this list into two equal parts. So this is my list. I'll make the letters bigger. See, every time what we are supposed to do is integer binary search. This is the algo. Array is the elements which will be there in the array, and n is the number of elements in the array, and key which we want to find, the element which we want to find in the binary search. So length will be equal low, that is lowest index will be equal to 1, and highest index will be equal to number of elements in the array. So I've written h is equal to n and L is equal to 1. So mid is equal to low plus high by 2. Then if key is equal to mid, return mid. If it is less than, then high will be equal to mid minus 1, else low will be equal to mid plus 1. Now, first of all, first condition for binary searching is that the list should be in the sorted order. As you can see, the list is in the sorted order. See now, this is integer binary search. I have explained the algo. Now we will implement it. These are the 15 numbers which are given to us. So how we will partition this list? First of all, this list will be partitioned from lowest index is 1, highest index is 15. So this list will be partitioned from 16 by 2, that is 8. So this is 8. There are two partitions which will having, first partition will have the elements from 1 to 7. Second partition will be having the elements 8 to 15. Right? Now let's find out. I want to look for the key 42. So my mid is now 8. This is my mid. Mid is now 8. So check whether if key is equal to A of mid. That is, if 42 is equal to A of 8. So A of 8 is 29. It is not equal. It is not equal. Now what to do? We have partitioned the list from 8. So 8 element would be there. One partition would have 1 to 7, another would have 8 to 15. Now check whether it is greater than A mid. 42 is greater than A mid. Yes. Then what to do? Make low is equal to mid plus 1. Make lowest index is equal to mid plus 1. That is 9. So low is equal to 9 and high is equal to 15. So 9 plus 15 upon 2. So this becomes 24 upon 2, that is 12. So 12 is the new mid part of 8 and 15 or 9 and 15. Fine. So at 12, you check whether 42 is there. No. So A of 12 is 47 and key is equal to 42. So it does not matches. Now we have to locate it. We have to locate it. Now it is smaller. 42 is smaller than 47. So make high is equal to mid minus 1. High is equal to mid minus 1. That is, your low will be 9 and your mid will be 12. So 9 plus 12 by 2. So this becomes 21 by 2 and it is equal to 10. And it is equal to 10. Now check at 10. Is 36 equal to 42? No. So now what to do? Is 36 smaller than 42? Yes. I mean 42 is smaller than 36? No. 42 is not smaller than 36. Now what to do? Your new mid is 10 and your high is 12. So partition this. So your new mid will become, L will become mid plus 1, that is 10 plus 1, which is equal to 11. 11 plus 12 by 2. So this becomes 22 by 2, which is equal to 11 itself. Now check whether A11 is equal to 42. Yes, it is equal to 42. That means you have found your element at middle position. See now, this is the middle part. So we are taking the tree. First of all, we have to break the entire tree into from the middle, that is from 8. Then one partition will have 1 comma 7 elements, another partition would have 8 comma 15 elements. Then this is again broken down. So 1 comma 7's mid is 4 and 1 8 comma 15 mid is 12. Fine. Now you find the mid of one partition will have the elements from 1 to 4, another partition will have the elements from 5 to 7, 5, 6 and 7. Fine. Similarly, here 8 was fixed, now 12 is fixed. Now one partition will have the elements 9 to 12, other will have 13 to 15. Now from this onwards, 1 to 4, middle is 2, 9 to 12, 5 to 7, middle is 6, 9 to 12, the middle is 10, for 13 to 15, middle is 14. Similarly, you keep on bifurcating and finally you will get the individual nodes. 1, 3, 5, 7, 9, 11, 13, 15 as the mid part. So that means we are breaking or dividing the list into the two halves until we find the key, our key, which we want to find at the middle position. So this is how binary search works and this is how the partition works. Now, see, if we want to search 29, 29 is at one comparison, means you have taken one comparison only. If I want to find 4 or 8, supposingly I want to find 4 or 12, that means I want to find 12 and 47. I want to look for key 12 and 47. How many comparison it will take? 2. Similarly, if I want to find 55, how many comparison it will take? It is at 15. So 1, 2, 3 and 4 comparison it will take. Fine. So to find 25, 25 is at 7th position. How many comparison it will take? 1, 2, 3, 4, 5, 6, 7, 8 comparisons. At every level, the comparisons are increasing. So if height of tree is given by log n, that means log to the power 16, because there are total 16 nodes. So 4 comparisons will be done at the most. Now, how many time complexity? Time complexity. If my element is found at the very first position, that means how many comparison it has taken? Oh, only one. Fine. So now if minimum time would be ON or order of 1, because if my element is found at 8th position only, that is I have bifurcated the list, I have found the middle and my element is found in the middle itself. So this is order of 1. Maximum time. Maximum time is the height of tree. It could be the last element in the tree. It could be at position 1, 3, 9, 11, 5, 7, 13 or 15. That means it will take order of log n time. Order of log n time, because I told you height of tree is given by, total number of nodes in the tree is given by log base 2 n. So log base 2 is 16. 4 comparison will be done in the entire tree. Fine. So it is equal to O log n, since the height of tree is given by log n. So time complexity will vary from order of 1 to order of log n. Next is bucket sort. First step, we will create the buckets. We will take the buckets. I will decide according to the numbers of element in the array how many buckets to be taken and assign the numbers to it. Second, apply the insertion sort to individual buckets. Then finally take out all the elements from the buckets. You will get the sorted list. Right? Now how this bucket will work? There are total 11 elements. So these are the elements 22, 45, we have 12, 8, we have 10, then we have 6, then we have 72, then we have 81, then we have 33, 18, 50 and 14. These are the 11 elements which we have. Total number of elements is equal to 12. So maximum is 81. You can see the maximum number element, that is the number with the maximum value is 81 and number with the minimum value is 6. First of all, create the buckets and assign the elements to it. I'll tell you how to assign the elements. Then apply the insertion sort to individual buckets. Finally, take out all the elements from the bucket and combine them. You will get the sorted list. Fine. So this is how this is how to assess the array. We will take the value I and we will assess the value of array. Now, there is one divider function. There is one divider function according to which the bucket sort is done. That is ceil function of max plus 1 by number of buckets. By number of buckets. Okay. Now, how to find the number of buckets? You have the minimum value 81 and maximum value is 6. So you see how many range is there, 6 to 81. Fine. So if I write 1 to 10 for 1 to 10 numbers in one bucket, then 20 to 30 in other bucket, then 30 to 40 in other bucket. So you will take the range from 1 to 90. So 90 divided by how many elements? 11. Roughly it is equal to, you may say 11. So we'll roughly take 11 nines or 10 nines are 90. Or you may take 10 buckets, because if number is not greater than 81, then it is okay. We can take 9 buckets. 9 buckets. If we are starting it from 0 to 9, total 10 buckets would be there. Total 10 buckets would be there. Actually, we have to take the range 1 to 90, then divide by 10. You will get 9 because total number of elements are 12. So you may have 10 buckets. You may have 10 buckets. Okay. So let's do it. So we will take two arrays. One to traverse this, we take two variables. So first of all, bucket one, you will write these are the elements ranging from 11 elements. So this is the array. So ceil of max plus 1 divided by number of buckets. So and number of elements is 12. Then you have max is equal to 81, min is equal to 6. Then you have buckets is equal to 10. And divider function we will calculate. So which is equal to max plus 1 is 81 plus 1 by 10, that is 82.10, then 8.2. So ceil is equal to 8. So this becomes the, sorry, you have to take the ceil value, so it becomes 9 because we have to take the uppermost value. Ceil becomes the 9. See, divider function is equal to ceil max plus 1 by number of buckets. 81 is the maximum number. 81 plus 1 is 82. 82 by 10 is 8.2. So when you take the upper limit, it will become 9. So divider function is 9. Now buckets are assigned from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I told you that there are total, we have total 9 buckets, but from starting 0, so it becomes 10. Now, how to assign the numbers to these buckets? First number is 22. So I'll do the calculation here, then I'll erase it. So this is the number 22. So the formula is floor of array I, which keeps on incrementing by divider. By divider. So divider is 9. So floor value of array of 0 is 22. So floor of 22 divided by 9, it comes out to be 9 2s are 18, then 9 4s are 36, and again 9 4s are 36. So you have to take the floor value, that is lowest 2. So assign 22 to bucket number 2. Assign 22 to bucket number 2. Next is 45. Floor of 45 by 9. Assign it to bucket number 9 5s are 45. So assign to bucket number 5. So this becomes the 45. Fine. Next number is 12. So 12 by 9 floor value. 12 by 9 becomes 9 1s are 9, 9 3s are 27, something like that. So assign 12 to this. Okay. Similarly, we can do it for all the values. 10. Floor of 10 divided by 9, 9 1s are 9. So this will become to first bucket, that is 10. Then 6. 6 by 9 will be 0. So assign it to 0 bucket. Then 72 by 9 is 8. So give it to 8th bucket. Assign it to 8th bucket. Next 81. 81 by 9 is 9 9s are 81. So give it to 8th bucket. Right? Next 33 by 9. 9 3s are 27. Then 6 left. Then you have 9 6 are 54. Then again so on. So give it to third bucket. That is 33. Then you have 18. 9 2s are 18. So give it to second bucket. Then 50. 9 5s are 45. Give it to fifth bucket. Then is number 4. Or I think it is number 14. Yes, it is number 14. So 14 by 9 is 1. So give it to first bucket here. You have 6 in bucket 0, 12, 10 and 14 in bucket number 1, 22 and 18 in bucket number 2, 33 in bucket number 3, 45 and 50 in bucket number 5, 6 and 7 left empty. In bucket number 8, you have 72, and in 9, bucket number, you have 81 number. Now perform the insertion sort individually on everyone. So what you will get here? You will get here 10, 12, and 14. Now you will perform the insertion sort 18 and 22 and 45 and 50. Now when you combine all these buckets, what you will get? 6. Empty bucket 0, you will get 6. Empty bucket 1, you will get 6, 10, 12, 14. Then you will get 18 and 22 after emptying bucket number 2. Then you have 33. Then you have 45. Then you have 50. Then you have 72. And then you have 81. This is how you will get the list in the sorted order. This is how you will get the list in the sorted order. Time complexity is order of n plus k, where k is the number of buckets which are used. Order of n plus k, because k is the number of buckets which are used to sort n elements. For sorting of n elements, you require the, it takes order of n time. Sorting of n elements requires the order of n time. This is how bucket sort is being performed on the numbers. See, worst time complexity, worst case complexity would be order of n square. Why? Because supposingly one bucket and there are two buckets which are having the elements, and there is a second bucket which is also having the elements. Suppose the list is divided in such a way that it is actually the elements are inserted into only two buckets, other buckets are empty. For example, it is having 10 elements. This is also having 10 elements. Now performing the insertion sort in this will take n time. Here insertion sort will also be performed on the individual bucket. It will also take n time. So that means one loop will be there for performing this function to assigning the buckets to the number, and second function will be performed in order to perform the insertion sort on the elements which are there in different buckets. So this becomes order of n square. First time is for the outer loop. First time assigning the buckets to the number, or assigning the numbers to the buckets, that would be more appropriate. Second time performing the insertion sort in the buckets individually. So your time will vary from order of n k to order of n square. This is average time, and this is your worst time. So this will vary from order of n plus k to order of n square. So because more auxiliary space is required for the buckets which we are assigning, instead of the numbers are stored in one array, and we are taking the auxiliary space for the buckets in which we are storing these numbers. So that is that will require the more auxiliary space. So it is order of n plus k. So thank you so much for this lecture. If you have any doubts and queries, you can ask the questions, or you can WhatsApp me your queries.